All right, so this is Algebra 1, Semester 2, going over Lesson 7.1 and 7.2. Uh, we talked about this before. I'm just going to do a couple examples, just a few examples of the examples that we already did. Uh, First thing that we talked about was zero property and negative exponents. And the first thing that we talked about was that any number that is a non-zero number, meaning uh, any number is not zero. So in the case of this, 4 raised to the 0 or negative 3 raised to the 0, any number raised to the 0 power is 1. Any number raised to the 0 power is 1, except for 0. We talked about uh, why that is. So 7.4 raised to the 0 power, also 1. And the reason why we talk about what that is twofold. So you have 1, actually let's start with 3. 3 to the 0 is 1, 2 to the 0 is 1, 1 to the 0 is 1. And if we was to further suppose with our logic that 0 to the 0 is 1, that would sort of make sense that 0 to the 0 power is 1. But there's sort of a counterexample to that as well. And that is 0 raised to some type of power. So if we have 0 raised to the third power, that's 0. If we have 0 raised to the second power, that's 0. If we have 0 raised to the first power, and that's also 0. And then if we follow the conclusion in the blue column, well then 0 raised to the 0 power is also 0. But in the world of mathematics, we can't have a situation where we have some scenario, in this case 0 to the 0, equal two different answers. And when we come across that in math, and it happens actually quite often, more often than you realize, you hit some type of anomaly, something that doesn't make sense. And when we do hit that in math and it doesn't make sense, we say that it's undefined. So when we do eventually say, well, what is 0 to the 0 power? We just say that it's undefined. So I'm going to write a circle with a little slash. That's called a null set, or in statistics, which is another fancy way of saying undefined, or you can also say does not exist. All these things mean the same thing. So any number raised to the 0 power is equal to 1 except 0. So that's where the non-zero comes from. Negative exponents. If we have a negative exponent, this negative does not mean that we're dealing with a negative number. This negative means that we're dealing with a reciprocal, meaning that the 7 goes in the denominator, and that number 7 is being raised to the third power. Once you do the reciprocal of your number, 7 to the third, and it goes to the bottom, the negative sign goes away. The book says negative 5 in parentheses to the negative 2. Again, this negative here does not mean that we're dealing with the negative number. However, this negative down here does. Go down in the bottom, and then that's squared. 7 to the third power is 343. and then negative 25 squared, or negative 5 squared is 25. So, negative exponents. If your exponent is negative and your number is in the numerator, then that means that you're going to go down in the denominator and it's going to go away. What if I had a number in the denominator? If I have a number in the denominator and it's being raised to a negative exponent, again, this exponent negative 2 means that it's the reciprocal, meaning this guy is not going to go in the numerator. And it's going to be 5 squared over 1, which is 25. So it doesn't matter if the negative exponent is in the numerator or the negative exponent is in the denominator. If you see it, you just flip positions. Whatever is in the numerator goes in the denominator. Whatever in the denominator goes in the numerator. I'm just going to do a couple problems, not a lot. So B, got it, number 1B, says negative 5 to the 0. Whoops, sorry. Remember that negative 5 is a non-zero number, so it's going to be 1. C has negative, or 3 to the negative second power. Remember that negative means that I'm dealing with the reciprocal, so it goes down in the denominator. The 2 follows it in the exponent, and that negative sign goes away, which is 1 over 9. And then I'm going to skip D and go to E, and I have negative 4 to the negative 2 power. Again, this negative has nothing to do with that negative. This negative in front of the 4 tells me deals with the actual problem itself in terms of it being negative. This negative with the 2 deals with the fact that it's going to be put in the denominator. So it's going to be 1 over negative 4 squared. Negative 4 times negative 4 is positive 16, so it's going to be 1/16. Simplifying expressions. So when you have I'm gonna look at number A. So A has x to the negative 9. When you have a variable raised to the negative exponent, the fact that I have a negative exponent tells me that this guy is not simplified. If you have a variable or any number where your exponent is negative, it is not simplified. So that means that I'm going to have to simplify it. And by simplifying it, all I mean is get rid of this negative sign in front of the 9. I know that that means that it's the reciprocal. So I'm going to write over x to the 9, and that's it. This is simplified. This is simplified. The 9 gets put in the denominator, the negative sign gets taken away, and we call that simplified. So for number B, letter B, we have 1 over n to the negative third power. Again, this negative sign means that we've got to deal with reciprocals, which means that this guy is going to go up top. So it's going to be n to the 3 over 1, which is just n to the 3. C, we're dealing with 4c to the negative 3 times b. Again, this negative 3 tells me that it's not simplified, that c is going to go to the denominator. However, there's no negative exponent by the b, there's no negative exponent by the 4, so these guys stay exactly the same and they stay in the numerator. So it's going to be 4b c to the third power. 4b c to the third power. And then for D, we have 2 over a to the negative 3. Again, This 2 has no negative exponent by it at all, so this 2 stays in the numerator. The a has a negative 3 in the numerator, denominator, so that means that this guy is going to flip up and go into the numerator. So this is going to be a to the third power over 1. So it's going to be 2a cubed. 2a cubed. So an expression is not simplified if the exponent has a negative sign in front. You have to get rid of that negative exponent by putting it in the denominator or numerator depending on whatever the reciprocal is, and then it will be simplified. Okay, solving these guys or evaluating, you can do it 2 ways. You can simplify the expression first, then substitute the number and solve, or you can substitute the numbers for the variables and then solve that way. Doesn't matter which way. I like to do method 2, which is to substitute first. Let's skip all the way to letter C. So C says n to the 0 over w to the 6. We're told that w is 5, n is negative 2. So negative 2 to the 0 over 5 to the 6. Negative 2 to the 0 is 1. And 5 to the 6 is 15,625. Alright, so D, we have 1 over n times w to the negative 1. Again, I'm going to substitute the numbers first, so it's 1 over negative 2 times 5 to the negative 1. This negative 2 has no negative exponents, so it stays exactly where it is. This 5 does, which means that this guy's reciprocal is going to move it up top. 5 to the 1 is just 5, and then the negative 2 stays on the bottom, and we have negative 2/5. Now, I'm not a big fan of the numerator and the denominator. I like my negative sign in the denominator. I like my negative sign in the numerator, but it doesn't matter. They both mean the same thing. Okay, and that's 7-1. 7-2 is going to be dealing with, did I pass it already? 7-2 is going to be dealing with multiplying powers of the same base. So to refresh your memory, let's say 3 to the 4. 4 is your power or your exponent. 3 is your base. What does the base mean? The base is the number that's being multiplied over again. The power tells you how many times you're multiplying it. The base is always the big number, and that's the number that's being multiplied over and over and over again, or a repeated multiplication. The power or the exponent tells you how many times. So when we multiply numbers that have the same base but different exponents, in this case we have 8 to the 3 times 8 to the 6. If we were to expand it out, it would be 8 times 8 times 8. if we were to expand this one out, it would be 1, 2, 3, 4, 5, 6. So we have 1, 2, 3, 4, 3 eighths here. We have 1, 2, 3, 5, 6, and I have a total number of 9. I have 9 eighths, or 8 raised to the 9 power. So what did I do? If you look at the exponents, I have a 3 and a 6. I could just add these guys up. So it would be 8 to the 3 plus 6. That would give me 8 to the 9th. I just add the exponents. This only works when the bases are the same. I repeat, this only works when the bases are the same. If the bases are different, you cannot add their exponents. So B has 0.5 to the negative third times 0.5 to the negative 8. They want it in base form, so that's just adding the exponents. So 0.5 to the negative 3 plus negative 8, which gives me 0.5 to the negative 11. 0.5 to the negative 11. C, we have 9 to the negative 3 plus, times rather, 9 to the second power times 9 to the sixth power. Again, that's just 9 with 2 plus 6 plus negative 3, which gives you 8 minus 3, which is 5, so 9 to the fifth power. 9 to the fifth power. Okay. Multiplying bases of algebraic expressions. So I'm just going to do B for this one as an example. We went through the first, all of these earlier today. B says negative 4 c cubed times 7 d squared times 2 c negative 2. So first thing I'm going to do is I'm going to put all the terms that are the same or similar with each other. So in this case, I have two sets of things that are the same. I have numbers and I have the variable c. D has no other variable for me to add or subtract with it, so I leave that alone. So it's going to be negative 4 times 7 times 2. Now the d's. D2, I'm sorry, not the c's. My bad. C to the third times c to the negative 2. And then lastly, d squared. 4 times 7 times 2 is 56 negative. I'm adding the 3 and the negative 2, so that's c to the first power, which is just c, and then d squared. First step, separate all the similar or like bases and numbers, multiply the numbers across, then you add the exponents of the same bases, and then combine them all together. They have a scientific notation one. I don't anticipate giving you a scientific notation on the test, type question on the test, so you don't really have to worry about it, at least when it comes to multiplying these out, so I don't really feel the need to go over that. 16 to the 1/4 power, so we're dealing with exponents that are fractions. So when you look at the denominator of an exponent that's a fraction, this number 4 is asking you what number, if I multiply it 4 times, gives me 16? What number, if I multiply it 4 times, gives me 16? And that number is 2. If I multiply 2 4 times, I'm going to get 16. Therefore, 16 to the 1/4 is 2, because that's the number I multiply 4 times. B, that gives me 27 to the 1/3. So I got to think of a number that when I multiply it 3 times, because my denominator is 3, if I multiply it 3 times, then it's going to give me 27. And that number is 3. 3 times 3 is 9. 9 times 3 is 27. So since if I multiply 3 times gives me 27, then 27 to the 1/3 is 3. And then (64). So this is C. If you have any number raised to the 1/2 power, 1/2 is the same thing as saying the square root. 1/2 is the same thing as saying the square root. So when you say 1/2, it means the same as saying the square root. So what number, if I multiply it twice, gives me 64? Well, 8 times 8 gives me 64. So since 8 times 8 gives me 64, then I know that 64 to the 1/2, or the square root of 64, is 8. Then the fractions gets a little bit more fun. So here they got 25, this is A, forgot it, number 5. 25 to the 3 halves. So I can sort of, the way that the book attacks this is that it says, okay, I can split, I have this 3 at the top, which means that I'm going to multiply something 3 times. So what the book says is, okay, let's multiply 25 to the 1/2 3 times. And then you're probably asking, well, why am I multiplying 25 to the 1/2 3 times? Well, if I was to do the math here, 25 to the 1/2, remember I have to add their exponents. 1/2 plus 1/2 plus 1/2 is 3 halves. So 25 to the 3 halves is actually equivalent. It's the same thing as saying 25 to the 1/2 times 25 to the 1/2 times 25 to the 1/2. They are equivalent expressions. So I'm substituting 25 times 1/2, 25 times 1/2 times 25 times 1/2 for 25 to 3 halves. So now that I look at that, I already know that this is basically saying the square root of 25. I know that the square root of 25, or the number that I multiply twice to get to 25, is 5. I can multiply those 5 3 times. 5 times 5 times 5. And it gets me 125. So I wrote the equivalent expression, 25 to the 1/2, and I did it 3 times because 3 is in the numerator of the original expression. And then I got the square root of 25, and then I multiplied it 3 times. 27 to the 2/3. Okay. So again, this 2 tells me that I'm going to multiply it 2 times, and it's going to be 27 to the 1/3. So the equivalent expression is 27 to the 1/3 times 27 to the 1/3. The 1/3, the 3 in the denominator tells me what number do I multiply 3 times to get to 27? we did that earlier, and that is 3. So 3 times 3 equals 9. So it's 9. And then 16C. 16C says 16 to the 3/4. So the numerator tells me how many times I'm going to multiply it by. So I'm going to multiply it 3 times, and it's going to be 16 to the 1/4 times 16 to the 1/4 times 16 to the 1/4. And from the earlier problem, we said that the fourth root, or the number that you multiply 4 times to get 16, is 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. So 2 times 2 times 2, and that gives me 8. Okay. Property, multiplying powers with the same base. Again, if you multiply numbers, exponents with the same base, you're adding the exponents. That's true also for when your exponents are fractions. Okay. All right, the last one, simplifying expressions with fractions. So let me do A, and then I'll do D, and I'll be done. So got it, number 6A says I have 2C to the 3/5 times 2C to the 1/5. Again, I'm going to separate out the numbers. 2 times 2. I'm going to have C here, and that's going to be 3/5 times C over 1/5. And that gives me 2 times 2 is 4. I'm going to add these fractions, and if they're fractions of the same denominator, I just add the numerators. So it's going to be C to the 4/5. So I multiplied the 2 times the 2 to get the 4. I multiplied the C to the 3/5 times C to the 1/5, and I add those fractions. 3/5 plus 1/5 equals 4/5, so I get 4C to the 4/5. Let's actually do C. So C, we have B to the 2/3 times C to the 2/5 times B to the 4/9 times B to the 4/9 times C to the 9/10. I'm going to put the b's with each other. So B to the 2/3 times B to the 4/9, because they have the same base, times C to the 2/5 times C to the 9/10. Okay, so I'm going to add 2/3 plus 4/9, but they don't have the same denominator. So this is looking at the B, the exponents for the B. What I do is I'm going to multiply top and bottom by 3, because 3 times 3 is 9. Top and bottom by 3. what I do to the denominator, I do to the numerator. So 3 times 3 is 9, 2 times 3 is 9, so this is renamed, 3 times 2 rather is 6, this is renamed 6 ninths. So 6 ninths plus 4 ninths gives me 10 ninths. And I'm going to do the same thing for the C's. I got 2 fifths plus 9 tenths. Here I'll multiply top and bottom by 2. 2 times 2 is 4. 4 times 5 is 10. So 4 plus 9 is 13. That would be 13 tenths. So now I have my fractions for my variables. So it's going to be b to the 10 ninths, c to the 13 tenths. Okay, so that was 6c. And I think that I'll stop there. So that was section 7.1 and 7.2. I'll probably be making some more of these in addition to maybe writing out some of my typewritten notes, and I'll also probably be giving out my notes on some of the answers on some of the exit tickets, so look for more of these to come. Alright guys, have a great rest of your day.